All right, let's get right into it. We've all had that moment, right? Staring at a physics problem, feeling totally lost. Well, today, we are going to unravel a real classic from Irodov's famous problem book. It's a fantastic puzzle because it mixes rotation, energy, and 3D motion all in one place. Let's break it down step by step.
So here's our game plan for today. We'll start by making sure we really understand the puzzle. Then we'll decode the setup, what's happening at the very beginning. After that, we'll pick out our physics tools, apply them to get our answer, and then most importantly, we'll wrap up with the key lessons you can take with you to solve any mechanics problem.
First things first, what is the actual puzzle we're trying to solve? Getting a crystal clear picture of the question is seriously half the battle.
Okay, at its core, the question is actually pretty intuitive. I want you to picture this. You've got a ball on a string. You pull it to the side. But instead of just letting it go, you give it a good kick, sideways. The question is, exactly how fast does that kick need to be for the ball to swing all the way up to the very top where the string is perfectly horizontal?
And here's how the Irodov textbook phrases it, in that formal physics language. We're on the hunt for that specific initial velocity, we'll call it v0, that allows the ball to reach a maximum angle of pi over 2. And pi over 2 radians is just 90 degrees, which is exactly that horizontal position we were just talking about. Now, before we even think about writing down a single equation, we have to visualize the starting conditions. Trust me, in mechanics, getting the initial setup right is absolutely everything.
Okay, let's walk through this sequence. First, the ball is just being held at some starting angle theta. But here's the critical part. It is not just released. It's given an initial kick, a velocity, v0. And you've got to pay super close attention to the direction of that kick. It's purely horizontal and it's perpendicular to the string. That one detail is what turns this from a simple, flat 2D pendulum problem into a much more interesting 3D problem.
So, with the setup clear in our minds, it's time to open up our physics toolkit. If we choose the right fundamental principles from the get-go, this whole thing becomes so much easier to solve.
So this is the question we should be asking ourselves. What is actually changing here? Well, its height is changing, which should make you think about potential energy. Its speed is changing, which points to kinetic energy. And it's moving in a circular path, which of course suggests rotation. So, what laws connect all of those things at once?
The answer lies in two of our most powerful tools, conservation laws. First up, we've got conservation of energy. It's perfect because it connects speed and height and lets us completely ignore the complicated path the ball takes. And second, to deal with the rotational part of the motion, we need conservation of angular momentum. Using both of these together, that's the real key to cracking this problem.
Let's start with the big one, conservation of energy. In this system, the only forces doing any work are gravity and tension. Gravity is what we call a conservative force, which is just a fancy way of saying energy isn't lost to things like friction. But what about the tension in the string? Well, the tension is always pulling perpendicular to the ball's motion, and a force that's perpendicular to motion does zero work. This is fantastic news. It means the total mechanical energy, kinetic plus potential, stays exactly the same from the start to the finish.
Our second tool is the conservation of angular momentum. Now, the trick here is being clever about which axis of rotation we choose. Think about torque as a kind of rotational twist. If we pick a vertical axis that goes right through the pivot point at the top, think about the forces. Gravity pulls straight down, so it can't create any twist around that vertical axis. And the tension? It pulls directly through the axis. So with zero net twist, or zero net torque, the angular momentum about this vertical axis has to be constant.
All right, we've got our tools selected. It's time to put them to work. This is where we start translating our physics ideas into the language of mathematics to actually build our solution.
We'll kick things off with energy. The principle couldn't be simpler. The total energy the ball has at the very beginning has to equal the total energy it has at its highest point. Let's write that out. Let's break down that initial energy. First, to make our lives easier, we'll say that the potential energy is zero at the very bottom of the pendulum swing. Now, a little bit of high school trigonometry tells us that the initial height is the length of the string, L, minus L times the cosine of theta. So the initial potential energy is mgl times 1 minus cos theta. The initial kinetic energy, that's just 1/2 mv0 squared. Add them together, and we have our total initial energy.
Now, what about the final state? Well, at the very peak of its motion, the string is horizontal. That means the ball is at a height L above our 0 point. So its potential energy is simply mgl. It still has some final velocity, we'll call it v. So its kinetic energy is 1/2 mv squared. The sum of those two gives us the total final energy.
And right here, this is a super important point. This is a common trap that a lot of students fall into. The ball does not come to a stop at its highest point. Yes, for a split second, its vertical velocity is 0. But remember that initial sideways kick? That means it's still moving horizontally. And to figure out that final velocity, we need our second tool.
So let's bring in conservation of angular momentum. By setting the initial angular momentum equal to the final angular momentum, we can find the missing piece of our puzzle, a direct link between the initial velocity, v0, and that final velocity, v. Okay, so angular momentum is basically mass times velocity times the radius of rotation. Initially, the ball is at an angle theta, so the horizontal distance from our vertical axis is L times sine of theta. That means its angular momentum is m times v0 times L sine theta. Now at the top, the angle is 90 degrees, and the sine of 90 is just 1, so the distance is just L. The angular momentum up there is m times v times L. Since these two have to be equal, we can cancel out the mass and the length, leaving us with this really nice, simple relationship. V equals v0 times sine theta.
Perfect. We've got our energy equation and we've got our angular momentum equation. Now all we have to do is put them together and solve for the one thing we're looking for, that initial velocity, v0.
Let's walk through the algebra. We start with that big energy conservation equation. First, notice that m is in every single term, so we can just cancel it out. Then we can simplify the potential energy parts a little. That gets us to 1/2 v0 squared minus gl cos theta equals 1/2 v squared. Now we just take our result from angular momentum, that v equals v0 sine theta, and plug it in. From there, it's just a matter of rearranging the terms to get everything with v0 on one side. We use that famous trig identity, 1 minus sine squared theta equals cosine squared theta, and we are almost there.
And there it is. After a quick square root, we have our final answer. The initial velocity you need is the square root of 2gl divided by the cosine of the starting angle. It's such a clean, elegant result, right? It only depends on the length of the string, gravity, and where you started from. So, we solved the puzzle. But you know, what's more important than just the answer is how we got here. What are the big strategies we can take away and use on other physics problems?
Okay, here are the major takeaways. First, always look for what's conserved in a system. It is almost always the easiest path to a solution. Second, really visualize the problem at the key moments: the beginning, the end, the top, the bottom. Third, never forget that forces like tension that are perpendicular to the direction of motion do zero work. Fourth, and this is a big one, don't fall into the trap of thinking an object has stopped just because one part of its velocity is 0. And finally, choosing your axes and coordinate systems wisely can turn a really hard problem into a much simpler one.
And that is our deep dive into this classic problem. We'll leave you with one final thought to chew on. We solved this in a perfect world with no friction. What would happen to our answer if we had to account for a non-conservative force like air resistance? That's a great question for another time. Thanks for joining this explainer.